Welcome back, everyone. We have a large square labeled A, B, C, and D. Inside the square, there's a zigzag path made up of 3 connected segments running from the top left corner, A, all the way to the bottom right corner, C. Along this path, we have 2 points, E and F. We're told that AE is 1 unit, EF is 2 units, and FC is 3 units. And there's one especially useful detail. The angle AEF is 90 degrees, and the angle EFC is also 90 degrees. Our goal is simple. Find the exact area of the entire square. Let's take this one step at a time. First, let's call the side length of the large square x. Since the area of a square is its side length squared, the area we're looking for is simply x squared. Now, here's the key idea. Draw a straight line from A to C. This is the main diagonal of the square. Notice that this diagonal crosses the middle segment EF at a point we'll call P. And suddenly, our complicated-looking figure becomes much easier to handle. We now have 2 small right triangles, triangle AEP at the top and triangle CFP at the bottom. Let's look carefully at these 2 triangles. They each have a 90-degree angle, and when 2 straight lines cross, the opposite angles are equal. So the angles at P are equal as well. That means the 2 triangles have 2 equal angles, and therefore they are similar triangles. That's the crucial observation. Now, let's use that similarity. The entire segment EF is 2 units long. Let the length of EP be A. Then PF must be 2 minus A. Because the triangles are similar, their corresponding sides are proportional. So the ratio of the bases must equal the ratio of the corresponding heights. That gives us A divided by 1 equals 2 minus A divided by 3. Let's solve that. Cross-multiplying gives us 3A equals 2 minus A. Move A to the left side, and we get 4A equals 2. Divide both sides by 4, and we find that A equals 1/2. So EP is 1/2 unit, and PF is 2 minus 1/2, which is 3/2. Now we know the 2 legs of each right triangle. Let's use the Pythagorean theorem. For the small triangle, AEP, the 2 legs are 1 and 1/2. Its hypotenuse is AP. So, 1 squared plus 1/2 squared equals AP squared. That gives us 1 plus 1/4 equals AP squared. Therefore, AP squared equals 5/4. Taking the square root, AP equals the square root of 5 divided by 2. AP equals the square root of 5 divided by 2. Now let's look at the bottom triangle. Remember, CF is 3, while AE is only 1. So the bottom triangle is exactly 3 times the size of the top triangle. That means its hypotenuse, CP, is also 3 times AP. Therefore, CP equals 3 times the square root of 5 divided by 2. And now we've reached the really satisfying part. We can find the entire diagonal, AC, It's simply AP plus PC. So AC equals the square root of 5 divided by 2 plus 3 times the square root of 5 divided by 2. Combine them, and we get 4 times the square root of 5 divided by 2. 4 divided by 2 is 2. So the entire diagonal is 2 times the square root of 5. Now we're almost there. Look at the large right triangle ADC. It is exactly half of the square. Both of its legs have length x, and its hypotenuse is the diagonal AC, which we just found. So one final application of the Pythagorean theorem. X squared plus x squared equals 2 times the square root of 5, all squared. That gives us 2x squared equals 20. Now divide both sides by 2, and we get x squared equals 10. And remember, x squared is the area of our square. So the exact area is 10 square units. A very satisfying geometry problem. If you enjoyed working through this one, give the video a like and subscribe for more elegant math problems. And I'll see you in the next one.